If my memory serves me, before the minor exam, the last lecture, we were discussing about measurable function as a background material for integration theory. Am I right? I think we just introduced the concept of measurable functions. Okay.
Yes, sir.
Let us quickly recall the definition and move on. Recall. An extended real valued function let us call f from E subset of R to R bar, where E is a measurable subset, could be R itself, and by R bar I mean R with the two symbols, plus infinity and minus infinity, is said to be measurable if there are variety of ways to define. I think this is how we define. If set of all x in the domain E such that f of x is greater than alpha is a measurable subset. Is measurable for each real number alpha. For each real alpha. Am I right? Is this the definition we took?
Yes, sir.
So this is the definition, but through a proposition, you have seen that there are many different ways to look at a measurable function. Okay. In fact, the following are equivalent. One, f is measurable. That means for each alpha, collection of all points in the domain whose function values are greater than this prefixed value alpha is measurable, or collection of all x such that f of x greater than or equal to alpha is a measurable subset. Lebesgue measurable, I mean. Or the collection of all x in the domain such that fx is less than alpha is measurable. And collection of all x such that fx less than or equal to alpha is measurable. These are all equivalent. And I think we have seen a few simple examples of measurable function. For instance, you have seen that constant functions are measurable. We also observe that the characteristic function on a set E, or the indicator function, the characteristic function standard notation is chi suffix E from R to R on set E. Characteristic function on set E is measurable if and only if the set E is measurable. So this gives you example of measurable function and non-measurable function. Once you have a non-measurable set, you have a non-measurable function. Just take characteristic function on the non-measurable set. It will give you an example of non-measurable function. So these are a few examples that we have seen. To add on, let me write one more trivial example. Continuous functions are measurable. So this gives you another class of measurable function. A continuous function extended real valued is also okay. A continuous function is measurable. I don't think I have listed this in the previous example, previous lecture. So how do you see that a continuous function is measurable? Let f from E subset of R to R bar is be continuous. You have to see, you want to see that f is measurable, so you can use any of these criterion. Let us go for the definition. And let us consider collection of all x such that f of x is greater than alpha, where alpha is a fixed real number. And this is actually the inverse image of the interval alpha comma infinity. Collection of all x such that f of x greater than alpha is synonym with f inverse of the interval alpha infinity for each fixed alpha in R. Now, do you see that this set is open? Which is open?
Yes, sir.
Because f is continuous, inverse image of a open set is open. And here you have open interval. Alpha infinity is an open interval, and therefore inverse image is open. Do you agree that open sets are measurable?
Yes, sir.
Yeah. And hence measurable. Remember that collection of all Lebesgue measurable sets is a sigma algebra, whereas collection of all measurable sets containing open set, the smallest sigma algebra containing open set is the Borel sigma algebra. And the collection of all Lebesgue measurable set is a sigma algebra containing the Borel sigma algebra. And hence, every open sets are measurable. So this proves that for each alpha, collection of all x such that f of x greater than alpha is measurable, and therefore, by definition, f is measurable. So continuous functions gives you a class of measurable functions. Okay. As I told you, measurability of a function is going to be a primitive assumption for Lebesgue integrability. Okay. Like boundedness of a function is the basic assumption for Riemann integrability. measurability is going to be a basic assumption for Lebesgue integral. You know that continuous functions are Riemann integrable. Yes or no?
Yes, sir.
And if you want an extension of Riemann integrability, you need to have every Riemann integrable functions as Lebesgue integrable. If you want Lebesgue integrable to be an extension of Riemann integrable, you need every Riemann integrable function to be Lebesgue integrable as well. So in particular, you want every continuous function to be Lebesgue integrable, later stage. For that, at the very minimum, continuous functions should be measurable. And that's what we have seen. Okay. Because measurability is going to be the standing assumption to define Lebesgue integrability. Are you with me?
Yes, sir.
Now, in line with the definition of a measurable function, let me make another definition, which we may not use quite often, but still, for the sake of record and exposition, let me make a definition here. This is very close to the definition of measurability of a function. We say that an extended real valued function is Borel measurable. F is Borel measurable or a Borel function if for each alpha in R, for measurability, what you need is collection of all x such that f of x greater than alpha should be measurable. Therefore, for Borel measurability of a function, what do you expect? What could be the definition? This set should be a
Borel set.
Borel set. Is a not just a measurable set, but it is a Borel set. Borel measurable set. Thus, for each fixed alpha, the collection of all x in the domain for which f of x greater than or equal to alpha turns out to be a Borel measurable set, then we call it as a Borel measurable function. Okay. We shall not discuss too much about it. Now let us move on to see some properties of a measurable function. As usual, after definition, we should develop a theory on it and then use those definitions for whatever we want to do. Okay. So we have defined measurable function. Now for some time, we will explore its properties, and later stage, we will use this measurable function for developing the integration theory. So that's our plan. So to move on with properties, I have the following proposition. Please recall that we have defined measurability in variety of ways. Fx greater than alpha is measurable, greater than or equal to alpha is measurable, less than alpha is measurable, less than or equal to alpha is measurable, and so on. Any of these things can be considered as a definition of measurability of a function. But if you see that list doesn't include collection of all x such that f of x is equal to alpha. What happens if that set is measurable? Okay, that's what the content of this proposition is. If f is measurable, then collection of all x in the domain such that fx is exactly equal to alpha is a measurable set. for each extended real number alpha. Not only for real number, it is true even for infinity and minus infinity. Each extended real number alpha. Okay. Before going to the proof of this theorem, I would like to draw your attention for the statement of the proposition. Just see the proposition. It is only one-way implication. If f is measurable, then this set, collection of all x such that fx equal to alpha is a measurable set. We are silent about the converse. Therefore, collection of all x such that fx equal to alpha being measurable cannot be taken as definition of measurability. Do you follow what I am saying?
Yes, sir.
Yes,
Greater
sir.
than alpha, greater than or equal to alpha, less than alpha, less than or equal to alpha. All these things can be considered as definition for measurability. But in view of this proposition, you cannot say if the collection of all x such that fx equal to alpha becomes measurable for each alpha, then the function is measurable. We cannot say. It's actually the reverse. If f is measurable, then this collection is measurable. Okay. With that warning, let us go to the proof of the proposition. Proof is fairly straightforward. Let us assume that f is measurable. Assume that's our hypothesis. F is measurable. F is an extended real valued function, and suppose it is measurable. What you want to do is to see that collection of all x such that fx equal to alpha is measurable. First, let us take alpha to be a real number. Let alpha belongs to R. And let us consider collection of all x such that fx is equal to alpha. Somehow, I have to conclude that this is measurable. I think you know the idea. You already know f is measurable. Once f is measurable, collection of all x such that fx greater than alpha, greater than or equal to alpha, everything is measurable. Keep that in mind. So how do I do that? Fx equal to alpha, I can write as
Intersection fx greater than equal to alpha
yes,
and fx greater than alpha.
yes. Thanks for it. Collection of all x such that fx greater than or equal to alpha, intersection collection of all x such that fx less than or equal to alpha. That's it. And by the measurability hypothesis, you know that these two sets are measurable. Since f is measurable, the sets appearing in RHS of the previous equation are measurable. So both the sets involved in RHS are measurable. And you know that intersection of two measurable set is measurable. And hence, the set in LHS is measurable. So this proves for every real number alpha, but the statement is for every extended real number. Now let us take alpha to be infinity. Minus infinity, you can similarly deal with. And I want to see whether the collection of all x such that fx equal to infinity is measurable. Again, whenever you are getting infinity, the idea is to write it as countable union or countable intersection. Okay. So let us take this as collection of all x such that fx greater than or equal to n for all n. So intersection of n belong to n, collection of all x such that fx greater than or equal to n. If fx is greater than or equal to n for each n, then you can interpret it as fx is equal to infinity. And you know that the sets involved in the right hand side are measurable. and countable intersection of measurable set is measurable. Okay, and hence I will just write and hence measurable. Similarly, for the case alpha is equal to minus infinity. So this proves the result that if a function is measurable, then the collection of all x such that fx is equal to a fixed extended real number is measurable. So obviously, it calls for a question whether the converse is true. Okay, so let us see by an example. Remark. So I would like to construct a function which is not measurable, but collection of all x such that fx is equal to a fixed number is measurable for each alpha. Okay, so that's my intention. So that I can say the converse of the previous proposition is not true in general. Let me first comment it. If collection of all x such that fx is equal to alpha is measurable for each extended real alpha, then f may not be measurable. So somehow I have to get a example where the function is not measurable. And as of now, what we know to construct a non-measurable function is to seek help from what?
Non-measurable set.
Non-measurable set.
So that we will do. Okay. So let us take the example as follows. Consider f from open 0, 1 or close 0, 1 doesn't matter. Let me take close 0, 1. Close 0, 1 to R, and let P subset of close 0, 1 be non-measurable. Existence of such a non-measurable set we have seen through axiom of choice and all. Non-measurable set. Okay. Now, how do I define my function? I define the function as follows. F of x is yes whenever x is in that non-measurable set inside 0, 1, and it is minus s if x is in 0, 1, but not in that non-measurable set. X Dirichlet-like function, but not with the q and q complement, but with the non-measurable set p and its complement in 0, 1. Okay. So this is my function, and now I have to claim that this function serves our purpose. Namely, this function is not measurable, but collection of all x such that fx equal to a fixed number is always measurable. Okay. Now, one thing that you can note first is that this function is injective. Do you see it? Note that 1, 1, I mean, note that f is injective. How do you see that? Fx equal to fy should imply that x is equal to y. Can you see it or not?
Yes, sir.
I don't think I need to write the explanation so that you can convince yourself. So why this injectivity will help. Therefore, if I take C, let C be in R, then collection of all x such that fx is equal to C would be equal to what? F is injective. Therefore, collection of all x such that fx equal to some constant will be either null set or a singleton
Or
set.
singleton.
Right? Is equal to null set or a singleton set. And hence measurable. Countable sets has measure 0 and measure 0 is of measurable type. If a set has Lebesgue measure 0, Lebesgue outer measure 0, then it is measurable. Okay. So the null set and singleton sets are measurable. Now I don't have to consider C equal to infinity and minus infinity here because those values will not be attained. So I don't have to consider set of all x such that f of x is equal to infinity. Okay. That means the collection that we are interested in, collection of all x such that f of x equal to c for varying c, various values of c are all measurable. Okay. However, f is not measurable. However, f is not measurable. Why? I will just write the reason. You can think over it. I consider f inverse of closed interval 0, 1. Can you tell me what will be f inverse of closed interval 0, 1? Look at the function. F of x is x when x is in P and it is minus x if x is in 0, 1 minus P. So I want to collect all those points in the domain whose f of x is in 0, 1. Yes? Who can help me?
The P.
It will be P. F inverse of 0, 1 means collection of all x such that f of x lies in the interval 0, 1. That is only when x is in P. Otherwise, it is minus x. Okay. So this is P and P is non-measurable, which is non-measurable. However, f is not measurable since the reason is this. How this can be a reason? Now, can you write f inverse of 0, 1 as intersection of set of all x such that f of x greater than or equal to 0 and f of x less than or equal to 1? Yes or no? Collection of all x such that f of x greater than or equal to 0 intersection collection of all x such that f of x less than or equal to 1 will be what? F inverse of 0, 1, right?
Yes, sir.
Yes.
So that intersection is non-measurable. That means at least one of those two sets is non-measurable. And that is enough to say that f is not measurable. Okay. So I am not writing the details. Or you can say that if f is a measurable function, then inverse image of every open set, inverse image of closed set, etc. will be measurable. So I will close the things with the definition now. Now we will develop certain properties of measurable function. First, my aim is to see that the collection of all measurable sets on a same domain, okay, is a nice set. It's an algebraically nice set. So first, let us introduce a notation. Let crypt f suffix e be the collection of all measurable functions defined on E. Our aim is to see that this set is an algebraically nice set. Okay, we shall see that. What do I mean by algebraically nice? You will come to know in a short while. We shall see that crypt Fe is an algebraically nice set. And in fact, it is not only algebraically nice, it will be topologically nice. When I say topologically nice, I mean with respect to limits and so on, they behave nicely. Okay. With respect to algebra, it behaves nicely. With respect to taking limits also, they behave nicely. Okay. We will make it more precise in the next theorems. So in that direction, we have the following theorem. Let f comma g be two measurable real valued function. Now I am not considering the extended real value. Two real valued measurable functions. With the same domain, functions defined on a measurable set E. Could be R itself or some subset of R. Then 1. F plus G is measurable. 2. C times F is measurable for each C real number C, and therefore you will get F minus G is measurable. So I will write F plus or minus G is measurable, and in fact Fg, the product, is also measurable. In this way, the script Fe, the collection of all measurable set, is algebraically nice. The first two gives you what? F plus G and F minus G are measurable, and constant multiple of a measurable function is measurable. So what's your conclusion about Fe? No? Nobody wants to answer? Am I audible?
Yes, sir.
Yes, sir.
So audibility is okay. Now, what about the answer? Do you want to answer my question? From the first and second part of the theorem, can you say something about script Fe?
So Fe closed under addition and scalar multiplication.
That is okay. That is just another way of saying 1 and 2. But can you say that it will be a vector space over R?
Yes.
Yes.
Collection of all real valued function defined on a set E is a vector space. Now you have these two properties. If f and g are measurable, f plus g is measurable, and whenever f is measurable, cf is measurable. Therefore, collection of all measurable real valued function will form a subspace of that. In particular, it is a vector space, right? So first two will give you that f script e, script f suffix e, I mean. The collection of all measurable function is a vector space. And what is third gives you? Whenever f and g are measurable, f plus g is measurable and fg is measurable. So you have a ring structure. Yes or no?
Yes, sir. Yes,
Yeah.
sir.
Yes, sir.
Therefore, the Fe is in fact a ring as well, with the plus and multiplication as Fg, point-wise multiplication. Okay. And in fact, it is a commutative ring. Fg is equal to Gf. It is not composition. Okay. When I say Fg, I mean the product. Fg of x is equal to f of x times g of x, point-wise product. Therefore, Fg is same as Gf, and therefore script Fe will be a commutative ring, and with the unity. It is a commutative ring with the unity. What is the unit element? You want Fg of x,
Identity function.
not identity function, constant function 1. You want f of x into g of x to be f of x itself for all x. So what should be my g of x? G of x should be 1 for all x, right? So the constant function 1, which is known to be measurable, is the identity. Okay. So the first two items tell you that this is just to recall certain ideas from algebra. The first two things will tell you that it is a vector space, and first and third will together tell you that Fe is a ring. Moreover, it is a commutative ring with unity, and unity element or identity element is the constant function 1. Okay, anyway. Now, without further ado, let us go for the proof. Proof is fairly straightforward, just 1 or 2 lines. However, for the sake of completion, let me write it. So you are given with the fact that both F and G are measurable, okay? And I have to prove that F plus G is measurable. To prove a function is measurable, out of that thing, I can prove that any of this. Either I can prove that collection of all x such that F plus G x greater than alpha is measurable, or greater than or equal to alpha is measurable, and so on. Okay. Now, first I think we can settle second first. Second item we can settle. That is more easy. Okay. Second I will prove first. C is in R, and let us call C to be greater than 0. Okay. Other cases, C less than 0 and C equal to 0, you can discuss similarly. Now let me consider the collection of all x such that CF of x is greater than alpha. And if this is measurable for each alpha, then I can say that the function CF is measurable for all C greater than 0. But this is same as collection of all x such that F of x greater than alpha by C. Division is well defined. I mean, that's why we put C greater than 0 condition, and inequality will be as it is because C is greater than 0. Now, since F is measurable, collection of all x such that F of x greater than beta is measurable for any beta. Okay, so this is which is measurable. Which is measurable. And therefore, CF is measurable. Similarly, you can consider C less than 0 and C. Similarly, for C less than 0 and C equal to 0. Okay. Now, let us discuss the first item. F and G are measurable, then F plus G is measurable. Okay. Let F and G are functions from E subset of R, where E is measurable to R. We are considering only real valued functions. Okay. Though measurability is defined for extended real valued, this theorem we are discussing only for real valued. We want to prove that be measurable. F and G are measurable. Okay. We want to prove that F plus G is measurable. And as you know, measurability of F plus G can be done in variety of ways. What I am going to do is, for this, we prove or we show collection of all x such that F plus G of x less than alpha is measurable. This is what I am going to look at for each alpha real number. Okay. How do I do that? It's not difficult. So let me call this set as A. Let A equal to collection of all x such that F plus G of x is less than alpha. Somehow I have to see that A is measurable. Okay. Now if x is in A, so for that I have to somehow use F and G are measurable. If x is in A, that will imply that F of x plus G of x is less than alpha. Okay. And that will imply that f of x is less than alpha minus g of x. Bear in mind that f of x and alpha minus g of x both are real numbers. We are considering only real valued function f and g. And between any two real number, there exists a rational number. Okay, there exists a rational number r such that f of x is less than r is less than alpha minus g of x. Okay, therefore, collection of all x such that f plus g of x less than alpha is contained in collection of all x such that f of x is less than r and collection of all x such that this r is less than alpha minus gx. I can write as g of x less than alpha minus r, where r can vary. Therefore, union of r in q. Okay. So collection of all x such that f plus g of x less than alpha, I could write as collection of all x such that fx less than r and collection of all x such that gx less than alpha minus r. And now this r can vary over q. Is that okay? Yes or no?
Yes, sir.
Now what is the property of q? Q is countable, yes?
Yes, sir.
Therefore, the set appearing in left hand side is measurable. Sorry, right hand side. Right hand side. It is intersection of two sets. Since f is measurable, collection of all x such that fx less than r is measurable. Since g is measurable function, collection of all x such that g of x less than alpha minus r is a measurable set. Intersection of two measurable set is measurable, and you have countable union of measurable set is measurable. Therefore, whatever you have in the RHS of that inclusion is measurable. What I will do is I will call it as B, equal to B say. Okay. Note that A is contained in B. Further, do you see that B is contained in A? What is B? B consists of all those set x such that, all those elements x such that f of x is less than r and g of x is less than alpha minus r for some rational number r. Rational number r. Since fx is less than r and gx is less than alpha minus r, fx plus gx would be less than
Alpha.
alpha. Therefore, it will be in A. So every element in B is in A. Therefore, in fact, A is equal to B. Thus A is equal to B. Further, B is countable. Sorry, B is measurable. B is measurable. Being countable union of measurable sets. Therefore, A is measurable. Therefore, A is measurable. Okay. And what is A? Collection of all x such that f plus g of x is less than alpha. And therefore, f plus g is a measurable function. A is a measurable set. Therefore, f plus g is a measurable function. Okay. So this proves that sum of two measurable set is measurable function is measurable. Now, what about f minus g? That follows from 2. Take c is equal to minus 1. You will get. Since g is measurable, minus 1 times g is measurable. And therefore, f comma g measurable function implies f minus g is measurable. Now coming to the last part, that leads us towards the ring. F and G are measurable implies product FG is measurable. Okay. For that, what I do is the following. I can write product FG as F plus G the whole square. So I will get F square plus G square, that I have to cancel. So minus F minus G square. So now I have 4FG, so 1 by 4. 1 by 4 or 1 by 2. F square plus G square plus 2FG plus 2FG I will get 4. Is that okay?
Yes, sir.
Now to prove that FG is measurable, I have to see that F plus G the whole square minus F minus G the whole square is measurable. But I already know whenever F and G are measurable, F plus G is measurable and F minus G is measurable. So what is only remaining is to prove that whenever a function h is measurable, if I can prove that h square is measurable, I am done. Yes or no?
Yes, sir.
We will do that. Okay. First we prove that. H from E subset of R to R is measurable, implies h square is measurable. Implies h square is measurable. X square defined in a usual way. X square acting on x is same as h of x square. Okay, that's the definition. How do I do this? How do I prove that x square is measurable? Consider the collection of all x in E such that x square x is greater than alpha. Okay. This will be equal to collection of all x in E such that h of x is greater than root of alpha. Of course, there is some assumption on alpha here. Union collection of all x in E such that h of x is less than minus root alpha. Okay. For alpha greater than or equal to 0. Is that okay?
Yes, sir.
Now, do you see that the sets in the right hand side, two sets are measurable?
Yes, sir.
Yes, sir.
Because h is measurable, right? Since h is measurable, it's very straightforward, but I have to write too many things. Since h is measurable, the sets in RHS are measurable. Therefore, collection of all x in E such that x square x greater than alpha is measurable. That's not enough because we consider only alpha greater than or equal to 0. Measurable for each alpha greater than or equal to 0. To call a function to be measurable, you need collection of all x such that that function of x greater than alpha measurable for all real number alpha. We could get only for non-negative real number. Now for alpha less than 0, collection of all x such that x square x greater than alpha will be equal to what? Can you tell me?
H square greater than 0.
And that is same as h square will be always greater than 0, right?
Yes, sir.
The domain.
The whole domain, that is E. I think H I took from E. Yeah. E. And E is measurable. By very definition, a measurable function has domain measurable, okay, which is measurable. Therefore, collection of all x such that x square x greater than alpha is measurable for each alpha in R. For each alpha in R. Okay. Therefore, H square is measurable. So whenever a function is measurable, its square function is measurable. Okay. So what? So now go back to this. F and G are measurable will imply F plus G is measurable, so square is measurable. F minus G is measurable, so square is measurable. Difference of two measurable function is measurable, and so on. And therefore, F comma G measurable implies Fg equal to 1 by 4 times F plus G the whole square minus F minus G the whole square is measurable. So this proves the result that we have stated. To supplement the result, let me make some note. First thing that I have already told you, we are having this theorem only for real valued function. Whereas measurability we can define for extended real valued function. Do you see why we are handling with only real valued function in this result? Do you see some reason?
Because infinity minus infinity will be not different.
Yeah, issues like infinity minus infinity will come. Suppose your f of x takes value infinity and g of x takes value minus infinity at some point, then you cannot define f of x plus g of x. Okay. So let me note down that. Now, for extended real valued function, f comma g, f plus g is not defined when at points where it is of the form infinity minus infinity. If fx takes infinity value and gx takes minus infinity, you cannot define f plus g. Okay, therefore, you cannot talk about f plus g at all. Leave alone the measurability, you cannot even talk about f plus g. However, product fg is measurable whenever f comma g are measurable. Even for the extended real valued case are measurable. Even for extended real valued function. This you can try to prove. Okay, product fg is measurable whenever you have two measurable extended real valued function. Maybe I will include this as a problem in the tutorial sheet. Now what I want to note is these these three items tells you that the script f suffix e is a algebraically nice set. Collection fe is a vector space over R. A vector space, and collection fe is a commutative ring. F and G are measurable, F plus G is measurable, Fg is measurable, that plus will distribute over the multiplication nicely and so on. It's a commutative ring. In fact, you can say that commutative ring with the identity. Okay. Thus, this is what I told. We shall see that script fe is algebraically nice. Next, what we do is to see that script fe is in some sense analytically or topologically nice. With respect to limits and so on also, it behaves nicely. Okay. So that's the next project. And to start with, Let us take two functions. Okay. So first, let me write this. Next, we shall see that script FE is topologically nice. That is nice with respect to process of taking limits. Okay, this is our aim. Towards this aim, let us start with the following. Let us consider two functions. Let us consider f and g. F comma g. Okay. To be measurable, let us consider f and g from E to R, f comma g measurable. I'm going to define a new function h, which I will denote as f join g. How do I define? H of x is you compare f of x and g of x at each x and take the maximum. H is f join g, where f join g is defined as maximum of f of x and g of x at every x. Okay, so every point you compare fx and gx and take the maximum. Okay, and similarly, let us define k to be equal to f meet g, where k of x is defined as at every point you compare fx and gx and take the minimum. Remember, fx and gx are two real numbers. And take the minimum. Okay. Then can you see that h of x and k of x are measurable? Then I will leave it as an exercise. H comma k are measurable. Functions. Convince yourself. Okay. How? We should be able to do this with the help of what we have proved. F and G are measurable. F plus G, F minus G, CF, F square, etc. are measurable. Okay. Somehow you use it and get it. Okay. Now, so what? Yeah. Once you can do for two functions, can you do it for finite number of functions? So if f1, f2, f3, etc., fn are measurable, you can say that f1 join f2 join etc. join fn is measurable. Okay. Now we can extend it for finite number of functions. That is, if f5 I is equal to 1, 2, 3, etc. up to n are measurable functions defined on same domain. Measurable functions on E, then join F5 I is equal to 1 to n and meet F5 I is equal to 1 to n. That is maximum of f1x, f2x, etc. fnx and minimum of f1x, f2x, etc. fnx are measurable. So far, so good.
Yes.
I don't know what you are thinking. You want to prove that f join G and f meet G are measurable. In fact, you can go by the definition. You consider collection of all x such that h of x greater than alpha. If h of x is greater than alpha, then f of x will be greater than alpha, the g of x will be greater than alpha, and f and g are measurable. Like that, you can prove it is not hard. Anyway, so now we have, if you have finite number of function, their maximum and minimum are measurable. Okay. Now we want to extend this. Instead of finite, let us consider a sequence. Let Fn n belong to n be a sequence of measurable function. Be a sequence of measurable function defined on the same domain. Measurable functions with same domain. Let us say E. Of course, E is measurable. Okay. Now I define their maximum and minimum. Now I can't talk about max and min. I will talk about sup and inf. Define sup n fn. This is a function. Okay. G equal to, and h is equal to inf n fn as follows. G of x, obvious definition. G of x is equal to supremum or fn x for each x, fixed x, n in n. And for each fixed x, h of x will be defined as infimum of the real numbers fn x, n in n. Please keep in mind that gx and hx can be infinity or minus infinity and so on, because we are not saying fnx are bounded, something like that. So this g and h are extended real valued function. Do you agree?
Yes, sir.
Yes, sir.
Now I want to see that g and h are measurable. Okay. Consider, I will just illustrate for g. Consider collection of all x such that g of x greater than alpha. By definition, g of x is sup this. Okay. So this will be collection of all x such that fn x greater than alpha for each n, union n in n. And each fn is measurable. Therefore, the right hand side union is measurable. Okay. Which is measurable. Which is measurable. And therefore, the new functions that you have defined, namely g and h, which are actually supremum and infimum, are measurable. Okay. Similarly, h is measurable. So I will conclude, thus g is measurable. Similarly, h is measurable. Okay. So we started with the two function. By induction, we can extend it to finite number of function. In fact, we could see that it can go for a sequence, and you can define sup and inf, and sup and inf as an extended real value functions are again measurable. Okay. Now we will push this further to taking limits. Okay. So, suppose we have a sequence of measurable functions. Sequence fn n in n of measurable functions. I'm going to define a new sequence Gn from Fn. Okay. Define a new sequence. This is known to you from real analysis, but let us recall. As follows. What I do, while considering Gn and Gn acting at x, what I will do is start from the nth stage of the original sequence. The original sequence is Fn, okay, and it starts from F1, F1, F2, F3, and so on. You discard the first n minus 1 terms and start from the nth term. That is, you consider fnx, fn plus 1x, and so on. Okay. And take its supremum. So start from the nth stage and find the supremum, and that is Gnx. Okay, and this is true for each n. And if you want to have a notation, it is supremum of fkx, where k is greater than or equal to n. While finding Gn, you will start from nth stage of the original sequence fn plus 1, and so on. So this is your Gn. Now, do you see that each Gn is measurable? If fn's are measurable, sup-n fn's are measurable. We already proved. So if each fn is measurable, do you see that gn's will be measurable? Yes or no?
Yes, sir.
We know that. I think I should not ask. I will keep on writing. We know that gn's are measurable. Okay. Being supremum. Whether supremum starts from nth stage or what, we don't mind. Supremum of set collection of functions are measurable. Okay, measurable functions are measurable. Therefore, Gn is measurable. Now, as n becomes large, what happens? Actually, as n becomes large, we are taking lesser and lesser terms. G1 consider F1, F2, F3, and so on. G2 consider only F2, F3, so on. G3 consider only from F3 onwards, and so on. So as n become large, we are taking only lesser and lesser terms, and therefore supremum will drop. Yes or no?
Yes, sir.
Yes,
So
sir.
what does it mean? That means we have a non-increasing sequence. Gn is a non-increasing sequence. Okay. Clearly, sequence Gn is decreasing. By decreasing, I mean non-increasing. Non-increasing sequence. Since it's a non-increasing or a decreasing sequence, you can talk about its infimum. Okay. Infimum Gnx exists. Now, here I have to be careful. When I say infimum exists, I don't mean it is a real number. If Gn is non-increasing and it is bounded below, then I can say infimum will be a real number. Here I don't have bounded belowness. I have only non-increasingness. Therefore, infimum will exist. Possibly that infimum can be minus infinity.
Yes,
Do you
sir.
agree? Yeah. Maybe minus infinity. That means when I say exist, I mean exist as a extended real number. Okay. So what is this infimum actually? That is infimum n over n. How did you define Gn? Gn was supremum. Supremum k greater than or equal to n fkx. Exist. Exist in R bar, which is equal to R union infinity comma minus infinity. And this is what you popularly call it as, what is this? Take
Limit
supremum
superior.
and then take
Limit supremum.
lim supremum. Okay, that is lim sup n tending to infinity fnx is defined to be, this is the definition, okay, infimum of sup fkx, k greater than or equal to n, infimum n over n. First take supremum, that supremums will be a decreasing sequence. Take its limit. Its limit will be same as infimum because it is a decreasing sequence. So first take supremum and then take limit. That's why the name lim sup, limit of the supremums. But the limit will be infimum because it is a decreasing sequence. Okay. Analogously, one can define lim inf n tending to infinity fnx. How do you define?
Supremum of infinity.
First, not minimum. You should not talk about minimum because you have a sequence. Minimum may not exist. Minimum and maximum make sense only when it is finite. Okay. So first you take infimums. Infimum of fkx. K greater than or equal to n. And these infimums will be an increasing sequence. Then now take the limit of that increasing sequence. But limit of an increasing sequence will be supremum. And when I say this supremum may not be a real number, it can be infinity as well. Okay. So now you got two new extended real valued function, namely lim sup and lim in. Okay. And do you see that both of this will be measurable?
Yes, sir.
Because supremum of a collection of measurable function and infimum of a collection of measurable function is measurable, and this limit is defined through infimum and supremum. Okay, clearly lim sup n tending to infinity fn and lim infinity fn are measurable functions. Are measurable functions. So we pushed further to limits. Two functions, finite number of functions, sequence of functions, now limit of the function are measurable. Now, when will you say that fnx converges? We know that the sequence fnx converges if and only if lim sup equal to lim n. Lim sup fn of x is equal to lim inf fn of x. Do you agree?
Yes, sir.
Real analysis. So what does it mean? If a sequence fnx converges, the limit function fx will be, sorry, and each fnx converges and each fn is measurable, then the limit function will be
Convergent.
I will repeat, if you have a sequence of measurable function fn and fn converges to f, then what can you say about f? F will be measurable because convergence means you can talk about limit. Limit means lim sup and lim inf are same. Yeah, already you have observed that lim sup and lim inf are measurable function. Okay, so let me write. Thus, if sequence fn are measurable functions and fnx converges to fx for each x in E as n tending to infinity, obviously, for each x tending to E, then the limit f can be treated as lim sup or lim inf. And you already observed that lim sup and lim inf are measurable. Then f is measurable. It looks very trivial, but it's an important fact. I repeat, if you have a sequence of measurable function and they are point-wise convergent, fnx converges to f of x, then the point-wise limit f is measurable. You got the point?
Yes, sir.
Now,
Yes,
why
sir.
it is important? Why it is important? You compare a similar result you have for continuous. If you have a sequence of continuous functions fn and fn converges to f point-wise, can you say f is continuous?
Need not, sir.
You cannot. You cannot say f is point-wise convergence will not say that the continuity will be maintained. Okay. Thus, we are in a more comfortable position than dealing with continuous function. In the case of measurable function, you can take limit, and the limit function is again measurable. Point-wise limit is measurable. Are you with me? So this is one of the reasons why later you will see that Lebesgue integration will have power compared to more power compared to Riemann. Okay, this is one of the reasons. I will explain it when that context comes. But right now, you should understand that as far as measurability is concerned, we are more comfortable than dealing with continuous. We are more comfortable position. Okay, because limits of measurable function is again measurable. Now I will just write compare it with sequence of continuous functions that point-wise converges. Continuous functions fn that point-wise converges to f. If you want to maintain the continuity, you require uniform convergence. But here, even point-wise convergence maintains measurability. Okay, so measurability is something that will behave with the limits. It is algebraically nice. In taking limit also, it behaves nicely. You can carry over measurability to the limiting process. Okay. Is that make sense?
Yes, sir.
Next, I will make a technical definition. This motivation for this definition will not be that clear now at this context, but later when we develop integration theory and so on, you will understand why this definition. Why is this definition needed? So now you just try to understand the definition without worrying about why we are making this definition. Okay. So it will you may feel this slightly out of context, but let me make it here. A property is said to hold almost everywhere. You say that some property holds for almost everywhere, and you abbreviate it as AE. Okay, you write it in short form, abbreviated as AE. Now, in measure theory, you will see quite often this one, AE. If, what is the meaning? What is the meaning of saying that some property is true almost everywhere? If the set of points where it does not hold, where it fails to hold, is small. The set of points where it fails to hold is small. Small measure theoretically means
Measure zero.
measure zero. To hold is a set of measure zero. Take a moment and understand the definition. If you want to call a property P is true almost everywhere, where it is not true should be having measure zero. The set over which that property is not true should have measure zero. Okay. For instance, in particular, suppose you have two functions f and g. You know that in set theory, you will say that f equal to g if f of x is equal to g of x for all x in the domain. Yes or no?
Yes, sir.
But now in measure theory, we will say that f equal to g almost everywhere if in particular f equal to g almost everywhere if f and g have same domain. It should have same domain, but you don't want f of x to be equal to g of x for all x, but you want only measure of all x such that f of x not equal to g of x. This measure should be equal to 0. Okay. I will give you an example. For instance, you consider this function f from R to R constant function 1. F of x is equal to 1 for all x. And you consider the function g from R to R. G of x is equal to 1 if x is in Q complement and it is 0 if x is in Q. Apparently, you see that f and g are not equal. Yes or no?
Yes,
Yes.
sir.
However, they are almost everywhere equal. Okay.
Yes, sir.
We note that. We just write like this. F is equal to g almost everywhere. Because you just look at f and g, where it differs. F and g differs only when x is in Q.
Rational numbers.
X is in Q. And what is the measure of Q?
0.
0. Because measure of all x such that f of x not equal to g of x is measure of Q, and measure of Q is 0. And you don't have to worry about whether measure or outer measure. Because if outer measure is 0, that set is
Measurable.
measurable. So
Measurable.
whether you write m star or m doesn't matter. M star is 0 means that set is measurable. Once it is measurable, you can talk about measure, not the outer measure. Okay. So this is what the meaning of saying something, two functions are equal almost everywhere means it is equal except for a set of measure 0. Similarly, you can say a sequence converges to a function almost everywhere. Let me write. We say Fn, sequence Fn converges to F almost everywhere. If what? There is a set E of measure 0 such that Fnx does not converges to f of x for all x in E. Is that okay? Where it does not converges, you collect those x, that should be of measure 0. We will not worry too much about this definition. I mean, why this definition is made, that will be clear when we start with the integration. Okay, I will give you an exercise at this juncture. Namely, yeah,
सर प्लीज इसका एक एग्जांपल दे दीजिए
please.
सर ये कन्वर्जन का कोई एग्जांपल दे दीजिए ना
Then you can construct. You please construct. Okay. Can you construct a sequence of function? For instance, again you work on R to R, and you can make a sequence of function which converges to f of x in Q complement, but not in Q. You try to do that. Okay. Anyway, these type of things we are going to handle not only as example but as theorems many times when we develop integration theory. That's why I told these definitions you may feel out of context now, but we will be using it. So you will get not one, quite lot of example of sequence Fn converging to F almost everywhere when I develop this course. Right now, I don't want to give. You can construct. Okay. You are very clever. Before writing the exercise, you are asking me. Okay. So exercise is 2 questions. One is a sequence of functions you have to construct so that Fnx converges to Fx almost everywhere. Okay. Construct a sequence Fn of real valued function such that Fn converges to F almost everywhere on R. That means Fnx does not converges to f of x should be on measure 0. It's really easy. You first consider a sequence of function Fnx converges to f of x for all x. Then you write your g of x and f of x as same except when it is of measure 0. Then you can say that Fn converges to g almost everywhere. Okay. First you take Fn converges to f everywhere. Then you slightly adjust your f to get a new function g. That's it. Anyway, and the second exercise is, suppose you have 2 functions f and g. One is measurable, f is measurable, and f equal to g almost everywhere. I want you to prove that g will be measurable. Let f be measurable, be a measurable function, and g is equal to f almost everywhere. Then prove that g is measurable. These are all very important in future. So in order to have measurability to be maintained, you don't want equality of function, even though they differ, but differ only in a set of measure 0. We can lift the measurability of f to measurability of g. We can carry over measurability of f to measurability of g. Okay. So I think now we are done with the background needed for the integration theory. As I told you, these measurable functions are the fundamental building blocks for integration theory. Okay. The next class, we shall start integration theory, but let me give you an overall view. Integration, just 1 minute. The integration that you know is Riemann, and integration that we are targeting is Lebesgue. Can you tell me what are the basic ingredients of Riemann integration? I'm not asking you the details, okay? The basic ingredient. You are integrating over
Domain.
intervals, not only just interval, finite interval. Length should be finite. You don't handle 0 to infinity or minus infinity, infinity, etc. in Riemann. Of course, that is improper integral. You can deal it with Riemann slight modification and so on. But as such, Riemann integral is defined only for finite intervals. Okay, finite interval or bounded interval. I mean, length is finite. And what type of functions you handle?
Bounded function.
Bounded functions, so that you can define small nk and capital Nk, infimum and supremum. And now the third thing is, how do you handle? What you do is, you take a bounded function. Rough idea is this. Okay, this interval AB, you subdivide into several subintervals. In the typical subinterval xk minus 1 xk, the function f will be approximated by a constant. You don't think that f varies, but you will assume that f to be a constant. In other words, you are approximating a function by a step function. Approximating a function f by step function. That means in x0, x1, you will assume that the function is some constant. In x1, x2, some other constant, and so on. Okay, that means you are, instead of dealing with the function, you are dealing with a piecewise constant function or a step function. Is that okay?
Yeah.
And
Yes,
in Lebesgue, what we are going to do is, instead of finite interval, you will consider measurable sets with finite measure. Measurable sets with finite measure. Later we will avoid this finite measure, etc. Okay, let us say measurable sets. Instead of bounded function, we will handle measurable functions. Maybe we will start with the bounded measurable function and then this bounded will be removed. And most crucial point is this. Instead of approximating the given function by a step function, we will approximate by simple function. So that's the difference. Of course, we have to handle this in a more detailed way, but just an overview. Instead of finite intervals in Riemann, we will consider measurable sets, not intervals. Instead of bounded function, we will consider measurable functions. And instead of approximating by a step function, piecewise constant function, we will approximate the given function by a simple function. Now, what is the next question? Look
what is
at
the same?
look at the Lebesgue side. Measurable set you know, measurable functions you know. What is unknown to you is? What is simple
Simple
function?
function.
So now our starting point for the next class would be, what is a simple function? How do you integrate a simple function? Once you have integration of simple function, how can you handle functions that are not simple using integration of simple function and so on. That's how we are going to develop. Now, those who have not read any book so far about Lebesgue integration, can you guess what may be the definition of simple function? I don't want answer from those who have read already. Can you anticipate what could be a definition for simple function? What is step function? You have an interval, you can divide the interval into several subintervals, and in each subinterval, the function is constant. Yes or no?
Yes, sir.
That is step function. Interval can be divided into subintervals, finite number of subintervals, and in each subinterval, you have a constant. Function is constant. That is step function. Now, keeping that in mind, what could be a simple function?
Sir, almost everywhere same as given function.
Don't have to complicate almost everywhere. See, instead of intervals, what you have?
Measurable
Measurable set. So this measurable set, you should be able to divide into several. You cannot call subinterval. Several
Non-measurable
sets.
subsets.
Subset. And in each measurable subset, you should have the function to be a constant. That's it. And that will be called as simple function.
Simple function.
So a simple function on a measurable set would be the given measurable set you can divide into finite number of measurable subsets, and in each measurable subset you have the function to be a constant. Such a function will be called as simple function. Okay, now instead of measurable set, suppose you have intervals, and instead of measurable subset, suppose you have subinterval, the simple function will boil down to
Step function.
Step function. That's what we needed. No, finally, we want to retrieve our Riemann. Whatever you do with Lebesgue, and when you want to retrieve it to bounded function interval, you should get back your Riemann. So keep that always in mind. That is how we will go for the generalization. So when you define simple function, instead of handling with the measurable sets and measurable subset, if you handle intervals and subintervals, you should get back my step function. So how do I define? So definition is already made. A simple function on a measurable set is that in which the domain measurable set can be divided into finite number of measurable subset, and each measurable subset, the function is a constant. Such functions are called simple functions. And step functions are one particular examples of
Simple function.
function. Okay, with that I stop. I mean, next class I will start detail with the simple function definition, more precise. But this is the idea. Okay, let me stop.